Have you ever held a small fridge magnet and felt that tiny snap against metal? Now imagine something so powerful it could erase every credit card on Earth from halfway to the moon, and that's still an understatement. The most powerful magnets in the universe aren't built in labs. They're born when stars die. And if one got too close to Earth, it wouldn't just disrupt technology, it could rewrite the physics of our planet. Let's interrupt what you think you know about magnets. The strongest magnet ever built by humans, created in a laboratory, can briefly reach magnetic fields of about 100 Tesla in pulsed experiments. That's already insanely strong. An MRI machine in a hospital runs at about 1.5 to 3 Tesla. Even the most advanced continuous research magnets barely exceed 45 Tesla. Impressive, right? Now here's the shock. There are objects in space with magnetic fields of 10 billion Tesla. They're called magnetars. Magnetars are a rare type of neutron star. And neutron stars themselves are already extreme beyond imagination. When a massive star, at least 8 times heavier than our Sun, runs out of fuel, it explodes in a supernova. What's left behind is a collapsed core so dense that a single teaspoon of it would weigh about 1 billion tons on Earth. Let that sink in. But sometimes, in very rare cases, the collapsed core doesn't just become a neutron star. It becomes something even more intense, a magnetar. Out of the roughly 2,000 known neutron stars in our galaxy, only about 30 confirmed magnetars have been identified so far. That's how rare they are. So what makes them different? Magnetars spin rapidly and have incredibly twisted magnetic fields. Their magnetic strength typically measures around 10 to the power of 10 to 10 to the power of 11 Tesla. To put that into perspective, their magnetic field is about 1 trillion times stronger than Earth's magnetic field. A magnetar's magnetic field is so powerful it can distort the shapes of atoms. Literally, it stretches them into thin, rod-like forms. Chemistry, as we know it, wouldn't function near one. And here's the part that sounds controversial, but is backed by physics. If a magnetar passed within about 1,000 kilometers of Earth, which is extraordinarily unlikely, its magnetic field would wipe data from every storage device and disrupt molecular structures in living tissue. Thankfully, the closest known magnetars are thousands of light years away. The nearest confirmed one, SGR 1935 plus 2154, is about 30,000 light-years from Earth. But magnetars don't need to be close to be dangerous. In 2004, a magnetar called SGR 1806-20 unleashed the most powerful giant flare ever recorded. In just a fraction of a second, it released more energy than the Sun produces in 100,000 years. The burst temporarily altered Earth's ionosphere from 50,000 light-years away. That's not science fiction. Satellites detected measurable disturbances in our planet's upper atmosphere. Pause. A star remnant halfway across the galaxy physically affected Earth. And scientists believe magnetars may also be responsible for at least some fast radio bursts, mysterious millisecond-long flashes of radio waves that release as much energy in a blink as the Sun emits in days. In 2020, astronomers confirmed for the first time that a magnetar in our own galaxy produced a fast radio burst-like signal. That discovery connected one of the biggest cosmic mysteries to one of the most extreme objects ever discovered. But here's something even more fascinating. Magnetars don't just have strong magnetic fields. Their fields are unstable. The crust of a magnetar is under unimaginable stress. When magnetic pressure shifts, the crust can crack in what scientists call a starquake. These starquakes release intense bursts of X-rays and gamma rays. Imagine an earthquake so powerful it emits radiation across the galaxy. And yet, magnetars don't last long. In cosmic terms, they burn bright and fade fast. Their ultra-strong magnetic fields decay over about 10,000 years, which is incredibly short compared to the millions or billions of years typical stars live. That means when we observe a magnetar, we're catching it in a brief, violent phase of its existence. Now here's a pattern interrupt. You might think black holes are the ultimate kings of cosmic extremes. They dominate gravity, yes. But in terms of raw magnetic intensity, magnetars win. Black holes can have strong magnetic fields in their surrounding disks, but the intrinsic magnetic field strength of a magnetar is unmatched anywhere else we know of in the universe. So why don't we hear about them as often? Because they're rare, and because they're quiet until they're not. Most of the time, magnetars are detected through X-ray and gamma-ray telescopes like NASA's Fermi Gamma-Ray Space Telescope and the European Space Agency's XMM Newton. They're invisible to the naked eye. No glowing spectacle in the night sky. Just sudden, violent outbursts of high-energy radiation. But here's the deeper implication. Magnetars may help us understand the limits of physics itself. Their magnetic fields are so strong that they push matter into regimes we cannot reproduce on Earth. Quantum electrodynamics, the theory describing how light and matter interact, predicts bizarre effects in such intense fields, like vacuum birefringence, where empty space itself behaves like a prism. In 2016, astronomers found observational evidence supporting this effect around a neutron star, confirming predictions made decades earlier. That means magnetars are not just cosmic monsters. They're laboratories for fundamental physics. And there's another twist. Some scientists are investigating whether magnetars could be linked to certain types of gamma-ray bursts, the most energetic explosions since the Big Bang. While long gamma-ray bursts are associated with collapsing massive stars and short ones with neutron star mergers, magnetar formation may power specific ultraluminous supernovae. The research is ongoing, but evidence suggests magnetars might be central engines behind some of the brightest explosions in the universe. So let's recap the scale. Human-made magnet, about 100 Tesla briefly. MRI machine, about 3 Tesla. Earth's magnetic field, about 0.00005 Tesla. Magnetar, up to 100 billion Tesla. That's not a difference of double or triple. That's a difference of billions of times stronger than anything we can continuously generate. And yet, despite their terrifying power, magnetars also play a role in cosmic creation. The heavy elements scattered by the supernova that forms a magnetar contribute to future stars, planets, and maybe even life. The iron in your blood and the calcium in your bones were forged in ancient stellar explosions. The universe destroys, and then it builds. So the next time you feel a tiny magnet snap into place, remember this. Somewhere in the Milky Way, a city-sized object with more mass than our sun is spinning, cracking, and unleashing magnetic forces so extreme they bend the rules of reality. And we're still learning from it. If this blew your mind, follow for more deep dives into the most extreme and fascinating phenomena in the universe. Explain so you can actually feel the scale of it. Now I want to know, if a magnetar is the most powerful magnet we've ever discovered, what other cosmic extreme do you think could completely redefine what we believe is possible?